I'm going to go ahead and get started, and people can trickle in as they see fit. Um, First of all, I wanted to go back and brush on yesterday a little bit. I apologize that I I messed up a little bit with that second piece of the code we were working with. My mind completely went blank that we could not run that code just using our own input because it was dependent upon a test file. I put some code together, both code that I wrote and stuff that I had from Lambda into one file that I dropped into the channel afterwards. And I tried to explain it as briefly, but as pointedly or fully as I could. If anyone has any questions about that code that I dropped the other day, what we were going over, uh, after you had a chance to work more with the sorts, after you had the QA, after you had the opportunity after hours, you worked on your independent project, post them now. I wanted to kind of just bring that up. If nobody had any questions over it, basically the main problem that existed is I had code in there, and because I had originally left out a line, like I mentioned at the end, that line is the comparison that specifically relates to a book object that's being created in that class that I added above it. And the entire test, which is just straight up Lambda code that I included at the bottom, is dependent upon that class. So I thought, when my mind went blank, I thought we could just feed it through a regular list of numbers or whatnot. And we could have if it would have changed that one line, but that was a mistake on my behalf, and I do apologize for that. So if anyone has any questions over that, you can ask now. Otherwise, we are going to keep moving with today. Today, we're starting the actual algorithms portion of the week and of the subject matter. Some of this is going to be a review over things we've already began to touch on. Some of this is going to be brand new. So I'm going to go ahead and share my screen. Hope everybody had the chance to review the pre-class material. And if anyone wants to ask anything about yesterday, type it in the channel now. Otherwise, I'm going to keep moving. You always can DM me later, but hopefully that's. I don't see anyone typing. So we got a lot to cover today. The rationale behind covering algorithms, make this real short and sweet. Programming is problem solving. We just had this discussion quite in depth in our staff meeting. It was related more to a discussion about difficulties that some people were having in general in the program. And first and foremost, programming is about problem solving. In this algorithm section, we will go over the Polya's problem solving again that we've already covered. And with problem solving, just like anything else, the more practice you get, the better you are. And these types of problems tend to show up in interviews. So something with front-end development, we just talked about this. I'm almost going to just steal the words of Brian Doyle, the instructor here. With a lot of front-end work, with a lot of, okay, I want this to appear on my screen. You can go to a tutorial, you can learn the technology, you can apply that technology, and you can write your program in whatever language or library or whatever you're trying to use. And that's how a lot of us get by. That's how a lot of us learn. With computer science, it can get a little bit more frustrating because there's not a tutorial on, it's easy to write a tutorial on how to do your first single page application in React. Plenty of those around. It's more difficult to write a tutorial on how to solve a problem, how to approach a real world problem and come up with a workable, efficient solution. So that is the rationale behind computer science. Is we need to, and we are going to work on problem solving, and that's going to be a big focus of it. We're also learning how to learn new languages, learning a lot of new concepts. But something to keep in mind here is one of the big things is learning how to solve problems. I think the big takeaways is that solving hard problems takes a lot of work and effort. It is doable with time and practice. It is doable if you follow something like Polya's. It is doable if you break the problem down into smaller problems. but it's a lot to learn. You're not going to be perfect at it, but I promise you, if you put the same effort into this that you put into web dev, if you put the same effort into this that you've been putting into all your learning endeavors up to this point, I promise you will come away with something valuable from it. I'm absolutely confident on that. I just got done writing in a cover letter today to a company that I'm currently applying for, how I felt my time as a TA really has strengthened me as a developer. It was an application for a front-end position, and I had several sentences on how I truly felt, and I wasn't bullshitting. It was actually, I was writing, I was like, wow, this is actually the truth that I'm writing. But I really do feel like both learning it and now teaching it has really strengthened me as a developer in many different ways. And if anyone's interested, I'm not going to go on talking about that right now, but if anyone is interested in hearing about it, feel free to hit me up sometime, and I'll give you exactly the reasons why I think computer science is important, why this has strengthened me, and why I didn't realize it until later on in the program when I was actually working here. So today we're going to talk about a general approach to problem solving. Hopefully, like I said, everyone watched the pre-class videos about runtime complexity and first pass solution. The first thing I want to briefly discuss within this module is, what is an algorithm? So does somebody want to write in your own words, one sentence or less, what is an algorithm? Put simply, what is an algorithm? Now I'm looking, it's like, is it an answer up on my screen? Because I've got the Lambda TK pulled up. What's an algorithm? Somebody type or talk. General, doesn't even have to relate to computers. An overall definition of an algorithm. Steps to solve a problem, almost exactly what I was looking for. A series of steps and rules to solve a problem. That is verbatim off some of the material Lambda supplies me. An algorithm can be short, it can be long, it can be simple, it can be complex. We know sometimes we write single line solutions to a code challenge. That's an algorithm. We know sometimes we have an algorithm that requires 100 lines, 200 lines, 300 lines. That is extremely complex. I remember one time Beej talking about a single query that he wrote in SQL, and it was something like, it was the equivalent of like 2 pages long, but it was just insane. And I think he shared it with us actually, but yeah, it's definitely can take on a lot of different forms. And there's a lot of real world examples of algorithms outside of JavaScript code or Python code. Somebody tell me some real world examples of algorithms that don't apply to computer science. We do them every day. We do them every hour. We probably do them every few minutes. There's always something we're doing. Tell me a real world example. A recipe, exactly. Making a sandwich. Yeah, a recipe. It is a series of steps and rules to solve a problem. The problem is I need to make food. The problem is I'm hungry, or I need to make food and I'm hungry. And it is a series of instructions that you follow systematically to solve that problem. Sorting laundry. Yeah, exactly. You've got to decide what the problem is. You've got to decide your constraints. How many different loads can I do? How am I going to sort these? One that comes to mind that is crossing the street even, which doesn't necessarily, isn't always intuitive because it's not written down there like a recipe or something, but it's kind of like the sorting laundry. It's something you're going through. The first step, look left. The next step, look right. The next step, look left again. If there's no cars, well, you can even say first step, look left. If no cars, look right. If cars, pause until no cars. Look left again, no cars. Look right, no cars. For me, look left once more, no cars, cross the street. So for us in computer science, of course, we know that it's going to apply to code. And I think the takeaway for the general approach to solve any algorithm is to use Polyas is the new way that we are going about doing this. And I'm going to drop a link here. I have to go look for it real quick. This is well worth your time to read. You should read all of this. We went over this. I think I dropped this last week when we discussed Polya. I'm going to drop it again. And we've already gone over it last week. I'm going to keep this brief today so we can move along to code. But remember, for any problem, we are looking to understand the problem and ask clarifying questions. My big takeaway, and each person may have an individual opinion upon it, my big takeaway is, can I put it in my own words? And like I think I said last week, there's a quote here at Lambda if I love, if you can't explain something simply, you really don't understand it. So first off, can you put it in your own words, and can you explain the problem to someone else? Ask the clarifying questions, whether it's to your colleagues, whether it's to your clients, whether it's to your instructors, whoever it may be, ask any clarifying questions that may help you reach a further understanding of the problem. Come up with a plan, write it out in sentences, comments, or pseudocode, the second part of the process in Polyas. Come up with a plan, pseudocode it out. How are you going to solve this problem? In this, break the problem down into smaller pieces. The next step, implement a first pass solution. The first pass solution being, it can be ugly. I don't encourage spaghetti code. I don't encourage intentionally doing anything ugly, for lack of a better terms, but it doesn't have to be a perfect solution. It does not have to be ideal time complexity, ideal space and complexity. The idea, get something that works. Whether it's in production, get something that works for MVP. Whether it's for a sprint, get something that works that gets you to the 2. Whether it is in an interview, get something that works that you can give to this person, because something that works is better than something that doesn't work. Come up with the first pass idea, and then we evaluate. When we evaluate, what kind of things are we going to evaluate? Remember, we talk about evaluate and iterate. What types of things would we look at in this evaluation after the first pass solution or after a second pass? What are some of the things we might look at? Type or write. It don't have to be technical terms. It can be in your own words. What are things, while we evaluate, after we've understood the problem, come up with a plan and implemented this plan for a first pass solution, what are things that we will look at to make this solution better? Anybody? I'm going to sit. So it's something I should do more, and I don't. I'm going to check if there's a way to do it more efficiently. Jawad, yes. What might we look at in specific? I'll throw out one to start this out. First thing we're going to do when we're evaluating and iterating is we're going to check for bugs. That is actually part of the evaluation. You should be doing this while you're implementing the first pass idea, because at least for me, I never can write code without constantly trying to run it, render it in the browser if I'm doing front end, whatever. But then in the evaluation, one of the first things you're going to do is fix bugs. Something we're going to talk about today, checking edge cases. Exactly. We might try to start thinking about those edge cases while we're coming up with a plan, but we definitely are going to check for more edge cases or all of the edge cases in the evaluation. Something else I think of, I'll let Jan wrong tie. Now we got some memory usage, space complexity. Exactly. And we'll talk more about space complexity. And with space complexity, what else is logical to mention here? Probably time complexity, and we're going to talk about that more today. Going to look for readability, redundancy. Can we make the code more dry? Have we repeated ourselves? Can we actually dry the code out? Do not repeat yourself. comment the code. Maybe we didn't get a chance to comment it so much, but it would be great at this point, if not already present, to comment the code to make it more readable. Maybe you came up with an iterative solution and now you can come up with a recursive solution that still falls within our confines of efficiency as defined by the project. So fix bugs, check the big O, check the space complexity, check the readability, check the redundancy. Yeah, check if we're covering all constraints and conditions, exactly. So we're going to do this, and then we're going to come up with that second pass solution, which we'll talk more about tomorrow. But I don't want to spend too much time on this. I want everybody to read this. If you haven't read it yet, read it when we're done today, at some point today. But just one time again, I want to iterate for all of this, whether it's for things we've already done, for sorting, for big O, for space complexity. It's practice, 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 and being methodical with the way you approach solving a problem. So today, our first example is going to be something simple, and I'm going to try to move through these fairly quickly, but I'm going to actually use, I was going to use the browser, but I'm going to use Python Tutor. It looks like it's pulling me into C. So we'll go to Python 3. Everybody aware of this site? Because yeah, if you're not aware of it, you're about to see it. So Python Tutor lets you use Python 3. It lets you use older Python. It lets you use C. So we'll be using C later. Mine, I think, is still defaulting to C because I was teaching C not too long ago. Probably need to clean out my browser, but it's nice because it allows you to visualize the steps going on in the code under the hood. So there are limitations. There's certain libraries that it does not allow you to use, but for the basics, it's great. For debugging, it's great. And first thing we're going to cover today, kind of a simple problem solving. We need to compute a factorial given a value. So in other words, just typing it, we'll say I want to compute 3 factorial. Who could the first step? What's the first step? If all I've told you is we need to write an algorithm in Python that computes the factorial of a given value. What's the first step of this? Understanding the problem. What would be parts of understanding the problem? I think the first real obvious thing is, do we understand what a factorial is? So somebody tell me what a factorial is. Doesn't have to be technical. Put it in simple terms. What is a factorial? If I say 5 factorial, what does that mean? Yeah, 1 times 2 times 3 times 4 times 5, yes. Product of all numbers from starting number to 1. Yes. So if we didn't understand that, we need to ask. If we don't understand the factorial, we need to Google. We need to talk to somebody. We need to do something to understand that. Pretty much in this case, it's so simplistic that that's really all there is. There's not a whole, some of the clarifying questions could, to me, the basics of this one is just understanding what a factorial is. So if the planning stage, if we were going to plan this out, I think a big takeaway from this might be, how are we going to solve this? Are we going to solve this iteratively, or are we going to solve this recursively? So in this case, let's say we're going to solve it iteratively. We could call this factorial. And our argument will be n. And let's just say I wanted to call return n times factorial of n minus 1. So if we put in a factorial of 5, if we substitute a 5 right here, Then our return says 5 times factorial of 5 minus 1. Return 5 times 4. Then we feed 4 into here. So we've returned 5 times 4. We've returned 20. We've returned a 4 here. And now we're going to return it. Does everybody see how this works? Eventually, what you're doing is simply returning 5 times 4 times 3 times 2 times 1 recursively. Yeah, thank you. I was waiting for somebody to mention that. So what should we put for that? If we just run it like this, it's going to throw it. It's, well, what is it not like?
I think you also need to add n. Yeah.
Yeah, it didn't. But it's going to throw an error because so if we were going to write the what would we put here? Because obviously this isn't going to work. What's the base case?
If or while statement.
Okay, if n equals 1, we're going to say less than or equals to 1. In case somebody puts in a n less than or equal to 1. We're just going to return 1. Remember, it's a mathematical fact, and this is kind of one of those edge cases. The factorial of 0 is 1. So if we get n is less than or equal to 1, we're simply going to return 1. Because the factorial of 1 times itself, factorial of 1 is 1. Factorial of 0 is 1. So if n is less than or equal to 1, we return 1. And then we simply return. Then we can say else return n times the factorial of n minus 1. And then we can just say factorial of, let's say, 5. And this is what's cool here is it lets you visualize the execution. You can play with this a lot more later. So it immediately jumps down to the invocation of the function factorial of 5, and it feeds it a 5. Goes to this, doesn't return 1, so it returns 5 times 4. Now we're running through the 4. And you can step through each of these and you'll see. Finally reaches the base case and returns 1. And you saw that the return value finally was 120 at the end. So 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1 is 120. So something cool you can do here is you can actually just run it and go back and you can just hit last and run to the end. You see that? So this is something you can play around with more on your own, but no, it's really cool because it lets you step through. If you have an iterative solution, it will step through every case of the iteration. Here it steps through all of the recursion. It's great for debugging. It's great for visualizing code. So when we are going to evaluate this, something that we can ask, because it maybe is not really, because this is such a simple case, there's not much else we can do recursively here to make this more ideal, but a question that can be asked, and remember, anything that can be solved recursively can be solved iteratively. ask, is there an iterative solution to this? And there absolutely is. How would we write this iteratively?
Create a for loop.
Create a what?
For loop.
Okay, do that. So, all right, tell me what you want me to type here. Say
For e in range 0 to length n-1.
right here.
Actually, not 0. Maybe 1 to yeah, length n.
Okay.
Oh, actually, no. Just for delete the range and put just n.
And n, remember, n is an integer that we're giving it.
Oh, it's an integer?
Yeah, we're not feeding this a list. We're simply saying define that. Remember, right here, we're just giving it an integer. So we can say, I think,
okay.
for e
yeah, range,
range
1 to n.
1 to n. Probably have to do something up here.
I think we can simply return.
What do you want to do?
Return just e multiply e plus 1.
Right here?
Yeah.
Remember that if we put in a return, we're going to return out of the entire function here. Maybe you could say,
okay, then answer equal.
is that what you were thinking? Something like that?
No, instead of that, I would say answer equal e multiply e plus 1.
E plus 1?
E multiply.
That's what it's going to be. So think about, we start with 0, and we're going to say answer, we set it 1 equals 1 times 1. Then this
Instead
iterates.
of answer, I would say, let me write it down.
I think this will actually execute. Ooh, what is this not doing? Yeah, so I was actually going to bring this up, and it's a funny syntax thing about Python, but if we were going to do it this way in a for loop, I would do this in a while loop, but I just wanted to let y'all do it the way you wanted to do it. While, and I would actually iterate at decrement. So I would start at n and decrement and say while, set up an iterator and say while it's greater than 0. But you have to do n plus 1 here because when you do range, it's not inclusive. So it's actually going to run from, like, say n is 5. This is going to run from 1 to 4. So you'd have to put n plus 1. And then you're saying answer is simply e times the answer, because you're just multiplying it times the next number, just like you're doing 5 times 4 times 3 times 2 times 1. Then you're returning the answer. And this is the correct solution, doing it this way. This way was a little weird because that for loop and that range, and I thought about it when we first did it, and that's what made me fix it so quick. But this is an iterative solution that we could use. Do you understand? Does everyone understand what I just did here? Because, see, Ilgar, you said answer equals e times e plus 1, but remember, because of this for loop and we're this range statement, you don't have to add. Yeah, now if you use the while loop, what we would do here is we could say while, we can say while I, we'll have a default of 1, while I, sorry, I'm just kind of writing this ad libs. So we would say while I is greater than 0, answer. I think you can write it like this, actually.
I think we need to increment somehow e.
The I. This is the incrementation you're talking about, right? So actually we started at n, so we're going to say minus equals 1. While I is greater than 0, answer is multiplied by I, and equals I minus equals 1, return answer factorial. I think this will execute, and we can say to the last, back, and we get the 120. Another way you could write this is simply while I is greater than e. Remember, that's the same as writing answer times I equals I minus 1. Same thing, but the same syntax we're allowed to use in JavaScript. And then the while loop, when it reaches 1, it terminates. It does not allow it to go to 0. And this is the iterative solution to that problem. Anybody have any? I'm going to post, actually. Make this anonymous. I am going to add choices, just yes or no. Type your questions if you don't want to type them in the channel. I'm putting this to the channel. Everybody answer real quick. Can you do a recursion using a while loop? No, because a while loop is iterative. A recursion is not iterative. A recursion is doing the same thing as iteration, but it's doing it by calling itself, and it's structured different. Yanrong, does that make sense? I'm not sure that I'm wording that clearly, but I'm not sure how to put.
I think we can use while with the recursion. Like we can say, instead of if, we can say while n bigger than 0, then do the recursion.
Yeah, you're right. You could define your base case with a while loop. So if we were going to do that here, we could say while I is greater than 0, we're going to call answer
I think answer a multiply and equal factorial n-1 would work.
The problem with this is, remember, with a recursion, you have a return, because the return is the recursion expands down the tree and then bubbles back up. You're returning each thing with the recursion. You can't really use a while loop as a base case because, okay, we're going to say while I is greater than 0, then answer, multiply equal factorial of n-1.
And you need to remove answer equal 1, because every time when you put something in the factor, it's going to make it 1.
You don't need that. You've got to set a base. You've got to initiate answer. So this would just be saying, if we gave it a 5, originally the answer would be equal to n, actually, and then you could say 5 times 4, and then it would feed it a 4. But then I promise you, there's not an easy way to use what this is. This is something you can ask in Q&A, but there's not an easy way to. You're trying to complicate something that already is complicated, and there's not a simple way to use a while loop in a recursion.
Could you just try make answer equal 1 and run this to see what's going to happen?
Do this right here. This is what you're saying to do?
Yeah, just run. Yeah.
I'm going to, recursion, a while loop is iterative. If you are trying to use that as a base case, you're going to run into a problem from the get-go, because in these other examples, like we were doing, we're returning the invocation of the function within the function. If you wanted to make this work, honestly, off the top of my head, don't even know how to make this work real quick. I don't know that if you'd like to come up with a solution and show me, show me. But I'm going to move along because we've got a lot to cover. But a while loop or a for loop is an iterative solution in general. A recursive case is something like we did, where we are returning the invocation of the function within the function. Two different things. Can you use a while loop while you're also using recursion? Certainly there's instances, but for the basics, no, this is not a simple way to do this. And like I said, if you can come up with a solution, I would be interested to see it and to talk about that. But for right now, I'm going to move along. And we can talk about one more, a great example, and something that we can talk about. Let's say we want to write a function to solve for the power. Given a value a and an exponent b, compute the value of a to the b. So given a and b, we're going to get a and b, a and b, compute A to the B. All right, so what are some questions? I think probably what are some questions that could come up here? What is the first step understanding the problem? Are there any questions that come to mind about this? What are some questions? Come on, guys. Yeah, I see some people typing. Cool. What are some questions? Will B be integer only? Great. Yeah, integer or decimal. If we got to deal with decimals, then we've got other implications that we might have to deal with in terms of the floats that we're getting. And kind of an extension of that may also be if we receive an invalid input, how do we handle it? And of course, the obvious one, if we don't understand the power, then we need to go back and reference, what are we talking about? A to the B, 2 to the 2 squared. And hopefully everybody, because of what we've done here, even if your math isn't strong, is aware of that. Is A and B passing in as array of data? We're going to pass it in as 2 integers. Ideally 2 integers. We're not going to deal with decimals, but that's it. How do we want to pass it in? We could pass it in as an array, but then you have to start dealing with accessing this will work to fact if n equals 1. Hold on a second. Let me look what you put. Oh, cool. Did you run that through and that runs out the?
Yeah.
Cool. Yeah, and like I said, I just wasn't sure because in general, we just write the base case at the beginning. But yeah, I definitely see what you're doing, and I like that solution. And n times factorial n minus 1. Yeah, that's definitely a good way. I don't know if I've ever seen it done like that before because, like I said, we generally just. Yeah, it's a little confusing. For me personally, it's a little confusing to think about because we're running a while loop within a function each time and we're invoking that function over and over and over again. And it's not like a while loop, but I can see how each time it doesn't violate the while and it simply returns. Yeah, I like that. But to me personally, that's a little confusing to think about. But it certainly does not mean that that's not a great solution. So thanks for
I
sharing
think
that. What's that?
recursion is general recursion is mind bending. It's if you add while, it's also get more complicated.
Well, this is the reason this is something me personal. This is not me trying to convince anyone of everything. So I see this while loop and I think, okay, this function is going to call itself and it's going to call itself and it's going to call itself. So if I have this while loop within this function and it's going to keep invoking this while loop and we're going to have, maybe 5, maybe 100 instances of this while loop is running. What are the implications of that? And I, in my mind, cannot simply think that out that, okay, without really sitting and thinking, all right, well, that the what? I'm just curious. And then we'll just invoke like I was doing factorial of 5. Now what the heck did I do? You see, we did create a lot of steps in this, a lot of additional steps.
So I used VS Code and it's working. I don't know.
Yeah, it's working. It's working fine here. It's got 26 steps in it, which is some more steps. But
could you check with the if statement to see if there will be less steps?
What do you want me to do?
So instead of while, if we use if, I'm curious if there will be less steps.
If I put if right here
instead of while, yeah. I don't know how was your original solution.
Nah, it's keeping it. I think I had one solution that I think was 15 steps. This does get this is a way to do it, and also another way to do it. We're getting into some. I've never seen some of these things done like this. Which this is interesting. I do want to move on though at this point with the next one. But yeah, you have taught me something new definitely, and brought up a good point that you can use these conditionals. But it's still in this case. I think it's adding a lot of the steps because you have. If you have the base case the entire time and you're calling the function, it has to pass through that base case each time. Here you're passing through of n equals to 1, return n, but then otherwise, or you could put else. Could you change that actually to an if?
No, it's just checking every time if n equal 1 and then run the other one.
Well, but then if it's 0, it's not good. If n.
For the factorial, we don't need the 0, right?
Well, but if someone inputs a 0, the factorial of 0 is 1. I think this might work. This brings it down to 6 steps, but does it actually get the answer? No, it doesn't. Oh, because if n is greater than 0, return n. If n is less than 1, less than or equal to 1, return 1, else return n times factorial of n minus 1. We can visualize this, and you got 22 steps. You do get the 120. But great points. I do want to move on. We're already at the hour. Actually, we're going to continue. I'm going to give everybody a 5-minute break, and we will go over this power, and then we're going to very quickly, and then we're going to talk about time complexity. So everybody come back at 7 after the hour, and I will see you then. All right. I'm back, and we are going to continue on. Nitel, I'm sorry if I missed your comment. You said just one if and return it. I did go back through this and look at all the steps, and whether you do, if you do it iteratively, it's 22 steps. If you do it recursively, the way I first did it, it's 22 steps. If you do it the way that Ilgar posted, it was 26 steps. That's getting real nitpicky about the number of steps. Basically, there's a lot of ways to do a single thing, and I think the takeaway is that, yeah, you definitely can use that loop to define your base case. I'm not sure if that really violates the spirit of recursion. That's a question you can ask in the Q&A, or that we could look into more later. But I wanted to move on to the factorial real quick, or to the, excuse me, the power. So we were talking about writing code to solve for, where did I see? Get A and B and compute A to the B. So if we were going to do this, and we were going to do this recursively, what could we do? We could say power, and remember we're taking in A and B in this manner. Can't type, so we could say if B is less than or equal to, what would we want to put here? If B is less than or equal to our base case, what would we want to stop this as? B is the power that we're raising it to. Remember from math that anything to the 0 power is 1. 2 to the 0 is 1. 1 to the 0 is 1. You can go read about that if you want to know why. Just the same as why the factorial of 0 is 1, but that's some complex math that's beyond the scope of what we're doing today. If B is less than or equal to 1, actually we're going to say if B is less than or equal to 0, that allows us to input 2 to the 0. But you could say less than or equal to 1 if you put less than or equal to 1. And return 1, and that would work. That should actually work as well. Either way, we're going to return 1, because if it equals to 1, and then if you put in a 0, yeah, we'll try it like that. And then we'll just have our else return. What would we return here to get the power? Remember, A to the B. What would we return here to solve? This would solve the problem. I'll start at A times, what would we return? Remember, we're doing this recursively, so we're going to call power. Yanrong, correct, but remember we're actually having to, where this is recursion, so we're calling, if you just put, the syntax you use is the simple syntax to actually get the entire answer. But for the, if we're trying to approach this recursively, say we did not have that syntax available both here in Python and in JavaScript, how would we do this? How is this working under the hood in Python? It's working, I would guess, with an iterative solution like we're working through. So we're going
to just pass A, power A.
And then remember we have two arguments. What do we want to do with B?
-1.
Yep. And that should be all that you have to do here. And then if we called power of 2 squared, we should expect a 4.
It still has the previous entry.
Why did this not work? The return value is 2, but 2 to the second power. So we did need it. It needed to be less than or equal to 0 on line 2. Yeah, it needs to allow it to, because of the nature of the math, it needs to allow it to go to 0. And then that actually, let's try this one more time. So if we said 3 to the third power, we would expect, 3 times 3 is 9 times 3 is 27. And you get 27. Of course, like I was showing earlier, you can walk through each of these and visualize the execution. That's something you can play with. And then you get that final return value of 27. But you see what you're returning each time. And that's kind of a nice little thing about this Python tutor. So what are the edge cases that now that we're trying to evaluate and iterate, somebody mentioned earlier thinking about edge cases, what are the edge cases we may need to evaluate here? What are edge cases?
Maybe someone will put negative, or yeah, like 2 power minus 6.
Yeah, that's a great thought. So what could we do to catch that? We could write an if, we could make our base case if b equals to 0, because if we're saying less than, then that's allowing all these negatives that we're trying to get rid of in, and then we could put an elif here, elif b is greater than 0, because we're looking for positives. Return the same, a times the power of a to the b minus 1. If we ran it just like that, this would still give us the proper answer. But to cover for the negatives, we're going to need one more line. So what would I start this line with? If, elif, what would I do for the negative exponent?
I think for negative, we need to divide the result to 1. 1 divide the result.
Divide the result, like 1 divided by the result?
Yeah. This is how the negative exponential works, but I don't know how to implement it.
So we could put else, and then we could say return 1 divided by a times power of a negative b minus 1. I need to close that again. And so let's
maybe
do
just b plus 1. Because negative 6, we want to make it negative 5, and then negative 4, negative 3. So
yeah, I'm about to run this and just see what it comes. So if I ran this with 2 and negative 1.
I know, actually, you're right.
Visualize this execution last back. Yeah, 2 to the negative 1. That's given the right answer. Does somebody have a calculator in front of them? We can put something complex in here.
Put 2 negative 3.
Negative 2 to the negative 3, like this. Two times 2 is 4, times 2 is 8. 1 divided by 8 is 0.125. Yeah, correct. So there we go. That's the correct way to do it. So good thinking on good math, and whoever came up with dealing with the negatives, this is how you would deal with it. So you're kind of seeing, we've thought about what else could be. We talked about an unexpected input. What would one of those unexpected input be? And someone asked, are we just going to deal with integers, or are we going to deal with decimals? And you can do these mathematically, but for this, we're not going to allow it. So what would we maybe do? Yeah. If we were going to allow something at decimals, something other than integers, there's a lot of ways we could go about doing it. But what we want to talk about right now is if there's a way to do fractional exponents, but we're not going to allow it. So we could go back in this code and we could say try val equals int b except value error. We just put a print. Everybody understand what this statement I did? The first thing it's going through is it's going to see, it's checking, is the value of b an integer? If it is, then, and then we're going to need a return as well. So if it does not pass this test, it's simply going to kick us out saying you must input an integer. Otherwise, it moves on to the code that we have. The code that we have also covers for, so if we ran this the same, we get the correct answer. If we run something like this, we get the correct answer. If we run something like try to run it. Oh. Hmm. We just went back and put it. Yeah, I'm not quite sure why this isn't wanting to run, and
because I think it's not it never catch, because we are saying if p equals 0, and it always put the run the else statement and keeps going. I think if you make the b smaller than equal 0, it maybe will work. Yeah, it returns 2 because 0.5 is 0, smaller than 0, and it returns 1, and just it makes it a 2 times 1 and return it.
yeah, but it's never catching here like it's supposed to. I'll get the correct code for this and figure out what is going wrong with this.
Could you post this?
Yeah, I will. I will post this right now. But yeah, I think if it's still getting it. For some reason, it's blowing up the stack in the recursive call because of yeah. I'll post this in there and we can. All right, so we're going to move along and take the last 30 minutes or so to talk about time complexity. When I find out what the error is in here, I have a feeling it's something small. I'll post it. If someone else figures it out, feel free to post it. We're going to talk about time complexity, and we've already talked about this to some extent, but with the big O and the time complexity, the takeaways from this and what we've previously covered is what big O and time complexity is at a high level, how common big O time complexities relate. And going back something, I'm going to drop this link right now for time complexity that I encourage everybody to read through. We don't have time to go through it piece by piece.
I think when you try to convert 0.5 to integer, it actually converts it.
That's normally, yeah, I'm going to go ahead and pass on this because we've got to talk about Big O. We can talk about it later on. That very well could be the case, but I know for certain, I know for certain how to write those in JavaScript. I'm not 100% sure that that's being written the correct way in Python. If someone knows it, I mean, because you can just type of it in JavaScript. Yeah, I don't know, but we're going to move on to the Big O as well for right now.
If you print value, I think
I'm gonna go ahead and I'm gonna pass on this right now. I'm sorry, but we need to move on with this, and we can talk about this after the hour if you want to stay on. We can certainly talk about this, but for the purpose of covering everything we need to touch, I need to move past it. It's more, basically the take home of all this is following that problem solving, defining these problems, planning the solution, implementing the solution, and iterating. Unfortunately, we got caught with a bug on the last one on the iteration, but the bigger take home is not how to solve this specific factorial problem or the exacts of the Python syntax for it, but it's working through this problem solving. And that's the big take home of today, but we definitely can talk about this after the hour. What I posted in the channel about Big O is something off of Stack Overflow that just says, a solid understanding of computational complexity theory, also known as Big O notation and or time complexity, is essential to design scalable algorithms, applications, and systems. Since scalability is highly relevant to computing and industry, Big O notation is too. Here, I'm going to drop this link. Is a great link that we've been using a long time here. It's the Big O cheat sheet. It gives you both a complexity chart with real simple with numbers and colors and all that good stuff to show you horrible, bad, fair, good, excellent, based on all the common runtimes. We will not even cover the factorial runtime or basically what we're going to concentrate on here is everything that you see here. O to the 1, O to the log n, O to the n, O to the n log n, O to the n squared, and briefly touch on O to 2 to the n. Beneath this, it gives a lot of different data structures, the different operations in the data structure, what the time complexity of it is, and also covers the sorting algorithms as well. So it's a pretty nifty little, pretty simplistic, but pretty neat thing to be able to look back on. The takeaway, I think, from this is keeping track of Big O when you code. It's not something that you're necessarily going to be doing all the time or something you're thinking of, every minute of when you code, but you've got to take Big O into consideration, and it will save you real life headaches because in real life, time complexity matters. Space complexity, which, like I said, we'll talk more about in the future, matters because this gets down to writing performant code. If you write code that gets an answer, that first pass solution, that's great. We got an answer. But what if it takes 15 seconds to return a query to a user? A user don't want to take 15 seconds to get a query, or a user wants it back in a second, 2 seconds, 3 seconds. So being able to understand the Big O notation, the time complexity, being able to analyze it, being able to apply it to your code is important. I kind of mentioned like a user query, but a couple people, can you mention real world examples where we may be coding where time complexity matters? Real world examples where time complexity matters. What are some real world examples? I talked about a query. So say on a social media post that's got 1 million users, it's something we'll actually cover later on next week, I believe. We'll be doing a social media mock-up, and we will see how operations with a lot of users can quickly become a problem. If we have to query 1 million different users and all their posts, obviously we can't have something that takes 30 seconds to return the answer. What are some other examples of runtime analysis? Police plate scanner. Oh yeah, got a lot of numbers to look at there. It's a great example, actually. Anybody else? Collision checking, which is something else we'll talk about next week in a gaming app for anybody that's into gaming. Collisions can definitely complicate your big O. How about registering someone on a website? And we're going to have to check whether that username and the email and everything else isn't already taken. Definitely there's ways of doing that quickly, and there's ways of doing that that aren't so operationally efficient. Yeah, Ilgar was typing about logging in. So instead of registering a user logging in and being able to. Logging in is a little bit easier because you're more just checking that specific username and that specific password, and it gets a little bit more complex with the security. But yeah, these are all good examples. And a lot of times why this matters in development, a lot of times here we're dealing with real small data sets. We're dealing with small inputs, and so it might work fine when we're developing it and we're putting in something small, but then in real life, when we move it to a production server and it's got a tremendous amount of data to handle, and we will see that in detail with a lot of code that we're going to play with next week. So this is why it matters, and I'm real briefly just going to talk about each runtime and some examples of these runtimes, and then we'll just go over an example of actually solving for these runtimes. Wait and see. Only thing I can think of is Uber. Oh, you mean that looking at a driver near you? Yeah. I mean, all of these examples are great examples of a lot of moving parts and a lot of users and a lot of data flowing in and being able to efficiently manage something like that. Was somebody else typing? I saw someone else typing. All right. Go ahead and move on. So obviously they've got excellent listed here, and the ones that fall within the range of excellent and good are O to the 1 time. O to the 1 is also known as constant time. A great example of constant time is accessing something in an array by index. It knows exactly where to go. No matter how big the array is, it's always going to be a single operation. It's going to be constant time. Other examples of constant time are assigning a variable to a value, performing a mathematical operation where it's, the input is n and the return is n times 1. Anytime that you've got, no matter how big your input is, that the number, remember when we talk about time complexity, even though it can directly relate to it, we're not talking about the time in milliseconds or seconds that it's running. We're talking about the number of operations that we are executing within the code that we're examining. We're looking at the number of operations, not the actual time, but the number of operations can have a large effect on the actual time. And of course, the actual time is what we're worried about in the end. But remember, we're dealing with number of operations. So kind of to jump over one, but O to the n time, who can think of an example that's something that is linear time? Linear time means each time that you add one new piece of data, one new element to an array, you add one more operation. What would be an example of linear time? Excuse me. Example of linear time. Good example of linear time might be iterating over a list. I keep saying array. I should be saying list for Python. Because every time you add a single element to that list, you're adding one additional operation, because instead of iterating over X amount of items, you're iterating over X plus 1 items. O to the log n. Remember the other day when we talked about divide and conquer? If you need more information on logarithms, go read about that. But remember, like I talked about the other day, there's that kind of large initial input, but then it actually narrows off. And that's because each time we're going through it, we are having our amount of data that we're dealing with in that divide and conquer, looking on each side of the phone book or the dictionary, looking something up, dividing our search into, or our sort into subarrays like we did the other day. But a great example of log n time is the divide and conquer. A great example of O to the n log n is a lot of the common sorting algorithms actually are in log n time. And that gets up into the range that's defined here as bad. Sometimes that's the best that you're going to get. And it's still, there's definitely a lot worse out there. O to the exponential time, O to the n squared. Anybody tell me what an example of O to the n squared would be? Something we commonly do a lot. I did it a lot in the beginning. Somebody tell me an example of O to the n squared. We all hopefully watched the video. What's a classic example of this? Somebody talk. Nested loop, John, yes. The nested loop. Yeah, wrong. I'm assuming you were talking about the log n for the phone book, but yeah, the n squared is a nested loop. What if we had a loop within a loop within a loop? Would it still be n squared? What would it become? Yep, n to the third. And then you can see why, yeah, O n to the third. You can see why we don't want to have nested loops, and the problem that sometimes you have to, sometimes we may be able to, but you can see in terms of time complexity, because for each element in the initial loop that we're running through, then we have to run the entire next loop. So when we add one more element to that array, you are exponentially increasing the complexity of that. Oh, 2 to the n, we're not going to talk about much. A great example of that is a password, and it allowing any character and adding the complexity of cracking a password is O2 to the n, because each time you add a character to that password, you create extremely more exponential possible combinations that could be reached, or that it would have to be tested, I guess I'm speaking in terms of cracking the password, and hence why passwords many times have a minimum length, or the suggested passwords are very long because of that. But just to go back over linear time, O to the 1, basically it's something like accessing an element in an object, accessing a specific, or accessing a value with a key in an object, or a dictionary as we call it in Python, accessing a specific index in a array, or as a list as we call it in Python. One operation, assigning variables. We'll talk more about that in the example I'm about to show, but anything that simply doesn't, no matter what the input is, the amount of operations do not change, is constant time. Log in, think of that as divide and conquer. If you need to understand more about logarithms, feel free to go read more about that, or ask me for some links, and I will find a good link. I had one at one point, but I don't have it on hand to read about how logarithms. There's a good Median article out there about it that I've used in the past, but I'd have to go find it real quick. O to the n, constant time. Each time the data increases, each time that array it has one more element, you add one more operation, so it's linear, just like a linear graph, straight line. N log n, a lot of the sort algorithms. Yeah, ideally you should try to avoid anything in the red. Ideally, you'd like to get, I would say ideally you'd like to see everything in O to the n, O to the log n, or O to the 1. That ain't always going to be the case. And sometimes you're going to be in the red, but ideally I would try to stay with I think, ideally everything would be in constant time, but in actual production, I think if you can keep it within this range, you're sitting pretty most of the time. And the other aspect that we'll talk about is sometimes space complexity matters more. Maybe the time complexity is not actually that great, but the space complexity, like we see with blowing up the stack in recursion, the space complexity matters because we've got a limited amount of RAM. We've got a limited amount of memory to deal with. So in the end, you're not only dealing with time complexity, you're dealing with space complexity, how you're going to balance what kind of weight you want to give to the importance of each one. So this is something, once again, that takes a lot of reps, some time to digest, some time to actually use. And like I said before, we will use this a lot in our actual live coding that we do. We'll talk about the big O of something. We'll talk about the space complexity of something. We'll talk about how we're going to improve it. We will do that a lot next week. This that I gave you would be good to read through. We don't have time to talk through all of this in class. But once again, like I was talking about, log, they have a nice chart here. The one time is also known as constant. This is known as logarithmic time, log n. Linear time is n. N log n is log linear. N squared. Well, they're defining it a little bit different here because they're going to call just simply n squared quadratic, n to the third cubic, and then 2 to the n exponential. Sometimes people refer to this as exponential because you are dealing with an exponent, but quadratic would be a good way. I think probably a better way to think of n squared, because a lot of times it's going to be n squared, n cubed. Like I said, they were showing you could think of it as cubic and so forth. And where the 2 to the n was the actual exponential, and then the one that they showed, the factorial, is something we're not even going to discuss because you don't want to do that. And I can't think of a time that I've really seen it come up. But this probably would be an ideal way to think of these in terms of the actual naming. But the concept is what's most important here. And we've got the same graph, basically, that we looked at earlier here, minus the colors and the good, bad, horrible. But the example we're going to do here, and you will have more examples in your independent project. You'll be expected to do this for the sprint. And this is something that we can go over this forever, but it's a matter of reps in the end that are really going to make you strong in this and affect your understanding of it. So, and I know all the answers here, but if we were going to solve, because there's a lot of rules that we're going to cover here that we didn't cover. If we were going to solve for this, actually what I'm going to do is I'm just going to cut and paste this so I can mess with it. And I'm going to go back to the browser, and I dropped this already, and I'll just put this in, and we'll just leave it like this. So we will go through this step by step. It's a fairly easy example, but this is a good example of how to assess the big O. Variable assignment, I mentioned this. What time is this?
Constant time.
Yeah, constant time. So we'll just say 1. And what's the next thing we run into here? This, I'll jump ahead and just say this is going to be constant time as well, because these are operations no matter, and there are ways to manipulate within here that can change the answer, but these simple operations that are simply based on I and J, and those are iterating in a linear way with integers, these are all just going to be 1. So we have nested loop here. What does that nested loop lead to? What does the nested loop, what runtime do we get with the nested loop?
N squared.
Yeah. So we can ignore this. We have 1s here. We have another loop. What time is this? A single, what time is a single loop? What is the time complexity? Yep, N. Thank you, Estevan. Add an element, we add 1. These are going to be 1 as well. This is going to be 1 as well. So the takeaway from all this is that, well, does someone want to tell me, someone that didn't maybe see the answer that I had posted up already, that in the thing, does someone want to tell me what the actual final runtime, if you were to be, what the runtime of this is? It's a pretty simple answer. Yeah, it's N squared. The reason for this is that no matter, we drop all the constants. So anything that we get that's one time, when anything else is involved, we drop the constants. Yeah, we have N squared and N if we had, even if we had another for loop beneath this right here, and it was N time, so you would have, in the end, you would have 2N plus N squared. You would completely drop this because this pales in comparison to the N squared. This is the dominant term. So whenever you've got a dominant term, the actual runtime is going to be simply that dominant term. And remember, we also drop, say if you had a runtime of 2N, that simply becomes a runtime of N because you drop that constant in front of it. You don't add these all together. Sure, this could actually be 3 plus, and then here you've got 4. We really don't take these into an account. What makes line 4 N squared and line 9 just N? Line 4, because it's also taking into account line 5. Remember, we've got a nested loop here. So every time we iterate through I, we've got to completely iterate through J as well. So if you add 1 here, it doesn't just add one single operation. You've got to iterate, it adds many more operations, and therefore it's N squared. Line 9 is a simple loop. So each time we add 1 to that integer input, we simply add 1 operation to that. Does that make sense?
Yeah, that clears it up.
Yeah, and right here they talk through the number of assignment operations is the sum of 4 terms there's our assignments here. The first term is the constant 3. Then the second term is 3n squared, because you have n squared and you have 1, 2, 3. Since there's 3 statements that are performed n squared times due to the nested iteration. The second term is 2n because you have 1, 2 right here, and an n like we had drawn out. Finally, the fourth term is a constant n because we've got this assignment again. So if you wrote everything out, you have 3 from here, plus the 3n squared, the 3 and the n squared, plus the 2 from here and the n, plus 1. Okay, I was looking at this. I was like, what happened? Plus 1 at the end. So that reduces down to 3n squared plus 2n plus 4. Remember, we could drop the 3 and the 2 and the 4. So now we have n squared plus n. We can drop the n. So we simply have O to the n squared. Any more questions about this? This is something that just takes some time and you're going to have to go over. I wanted to go over a simple example and the kind of the down and dirty of the big O, again, what it represents, what it's used for, real world examples of it, how we determine it, and some graphic and practical representations and talk about it. Any specific questions over big O that we've just covered? We're running out of time here, but anybody that's got any questions or just any questions over today?
Yeah, John, I'm just curious if for your second for loop, you had another nested loop there. What would the runtime be?
What if you had an n? If you had
Right.
another.
If under that you had another loop.
Oh, so you mean like, right, if you went back here, if we nested another loop here, right?
Yeah.
So then this would become 2n squared plus 2n, or what would you have? 3n squared plus 2n squared. You'd have 3n squared plus 2n squared. So you would have 5n squared, and that still is n squared.
So because we're dropping the what is it called, coefficient, it's still going to be n squared.
Yeah, you're dropping the leading coefficient. You're executing the math, the basic algebra and the math on it. You will end up like we did up here with 3n squared. You will have 2n squared here. So 3n squared plus 2n squared is 5n squared. We drop the leading coefficient because in the big picture with a huge amount of data, yeah, it matters. Like I said, we were nitpicking with the 22 versus 26 operations, but in the big picture, obviously this computer is capable of running billions of operations within a very short period of time. So in the big picture, that n squared mattered. If we suddenly had a term in here where say we added 2 we then had 2n cubed plus 3n squared plus everything else, it would simply be n cubed because that is the dominant term.
Gotcha.
The reason earlier, like that you're able to come up with something like n log n is because you were multiplying those two. So because that's all happening in one line, you're multiplying the n times the log n. There's a significant difference. We don't drop the n in front of log n and n log n because there's a significant difference between n log n and log n. There is not a significant difference between 3n squared, 5n squared, 3 plus 5n squared. But then if you said 3 plus 5n squared plus n cubed, there is a significant difference between n cubed and the rest of it. The idea is to come up with something as simple as possible within as small of a range as possible, but as practical as possible. And like I said, a lot of these take reps. They get a lot more complex than this. But that's kind of the basis of it, and we will cover this a lot more in the future. Were there any more questions in general about today? I wanted right now, because that question came up earlier, with the code that I dropped where we were trying to get this to run. Does anyone want to stick around and work on that? I know everyone's free to go to lunch. Yan Rong, if anybody wanted to talk about it or if anybody wanted to mess with it, like I said, and post the solution later, I'm certainly going to look for the answer of why this didn't work. Otherwise, everyone's free to go. I will post the video. Everyone should have the repo. If you don't have the repo, I can post that real quick. Remember, to follow the workflow. Anyone doesn't have it, all of the videos for tomorrow are still in the pin that I've got right here. So there's all your videos. No, I didn't. I lied. I'll go back and find where I thought I pinned it, but I guess I didn't. I may have posted these in my group channel. I did. And anytime that you don't see, I forget sometimes and I get the channels mixed up. If I don't have the videos posted in the channel, definitely let me know. But these are all the remaining videos. The videos for the entire week, what the names of them were, when they were for, and whether they were optional or not. So the videos for tomorrow, hopefully you've already looked at, but you see the ones that are required. All of them are required for Thursday. Now everybody has it. Like I said, somebody speak up if I do forget that, because occasionally I'll post something in one channel that I mean to post in another channel. But you got the videos, you've got the link to your repo. You know the workflow for getting your repo set up. Add your PM as the contributor or the collaborator. Do your pull request. I don't have anything else. Tomorrow is algorithms again, and we'll go over second pass solutions, improving on that first pass solution. Other than that, I'm going to let people go. Get on with your lunch. We're past our time. If anyone has anything for me, you can DM me, post it in the channel. And remember, use the help channel, use the 20-minute rule, use your PMs and TAs, and don't be afraid to reach out for help if you need anything. So thank you, everybody. I'll get the video posted. Now I've got the videos in the correct channel for the week, and you've got your repo. So I'm going to go ahead and